Okay. Hi, everybody. My name is Yao. I'm Wang, and I'm working for Fluent Labs as a ZK engineer. Today, I'm going to talk about BNews and a protocol based on BNews. So, what is BNews and why it is interesting for us? So, okay, there are two papers. The BNews are a series of papers, two papers made by a company named Irreducible. I mean, you can see the name is Urutavena, but they renamed as Irreducible. And they produced two papers. One is, the first one is introduce the idea of binary tower field. And the second one is building, so they built a multilinear commutative scheme from this in the first paper. It's the ideas they introduced lots of interesting ideas, and then they write a second paper showing okay you can actually do FRI like stuff over the binary field, and it will give you some pretty good result. So today I'm going to talk about three parts. So the first part is going to be what is binary tower field. Okay. And the second part is going to be why it's a good. I'm going to show why it is very hardware compatible, and compared with Merson field. A third part, I'm going to talk about one ingredient in the second paper that how you can see it as it can provide you a folding like in FRI. It's slightly different, but it's the authors they make a protocol out of it. Okay, let's start with binary tower field. Okay, I guess everybody attended the finite field workshop, so I don't need to start with finite field. Let's start with this. So binary tower field. Okay, so let tau. This is a capital Greek alphabet tau. 0 equals F2. So now what we want is take a field extension of this tau now. Tau 0 is, let's take tau 1 is F2 with x, where x satisfies this equation. Okay, let's call it x naught because we're going to have a lot of variables. X naught squared plus x naught plus 1 equals 0. And so this will be our first, a little bit larger field. So this will have 2 elements, and this will have 4. And we can continue with this we call Toyota equals Toyota. This is iota. Okay, I don't know how you write iota, but that's how I'm going to do it. With x iota minus 1 Okay, so if you actually study the finite field, then you can see that we have a tower of field, like tau 0 is included in tau 1, included and tau iota. So in field theory, this is called a tower of field. So you have this inclusions Yeah. So how big these things are, and this, if we can count this as 2, which is 2 to 0. This will be 4, which is 2 to 2. And this will be 2 to 2 iota. So,
sorry, 2 to 0. The first.
Okay, 2 to 2 to 0. Okay. So if we think about these things and we want to represent them on computers, so let's count about digits. What this effect is saying that if you want to represent tau 0, you need 1 bit. And for tau 1, you need 2 bit. And if you want, okay, this will go like da da da, 32, 64 bits. So every time when we go up one level, we need to double the bits. And so why they are good? Okay, so they are good because they have very nice property when you compute the addition of and multiplication. Okay, I'm going to tell you that addition is just a big XOR. So effectively, you don't really need to do something boring thing called carry if you want to add these two numbers, which represent in these binary strings. What you do is just do XOR. It doesn't matter which level they are. And also, there's a very nice thing about, I'm going to talk about later, is that embedding. So each level embedding the next, the higher level in a very natural way, which effectively you do not have any extra effort to do the embedding. Okay. There's also the multiplication. It's actually very good. Okay. So multiplication is 2 to iota to log 3. This is almost something around here. So why this is good? Because if you think about it, this is essentially a 2 to iota dimension. So you have 2 to iota branches to compute. If you want multiplication, you have to do a 2 to iota times 2 to iota things. So for naive, you got, I believe here should be 2, but then what the result is that after some analysis, if you use something called Karatsuba, you get this. And this is much better than, so 1.5 is much better than 2. So they are good. Okay, so I'm also going to show you that how this embedding works. So let's say we have alpha in f2 to iota plus kappa. So this is a big element here. I'm going to show you how to do it here. So alpha has a 2 to iota plus kappa bits rep. And let's represent it in here. So we can group A's representation. So this will be a concatenation of strings. And we group them into 2 to kappa many terms, and each term will contain 2 to iota bits. And you will see that each of them are your, let me think. So each of them are your representation of the coefficient in the vector space based on this. So what I'm saying is that if we have a string of this alpha in the big field, you can go down wherever you like to write it down as the summation, as the you can get the information of how you represent this thing here by just reading the strings. So these are the coefficients. Just so if you have, let's say you need, so you have two kappa many components, and each component will be your, okay. So, right, I think I have to talk about how do you write, okay, so what's the basis of this? So the basis of this will be, this is something I forgot. So basis the F2 basis will be one, so these are the degree 1 terms, and these are the degree 2 terms, and and in the end you get everything multiplied together. And this will be the 2 to iota. So we will have 2 to iota many vectors and these elements, and these will be the basis of our field. And how is, since this is a F2 basis, so everything is just you pick them or not picking them, you have, in the end you end up these many choices, you get the whole field back. So, okay, so this will make a very very simple introduction to the binary tower field. And so the question is, why do we care binary field? And the reason is that they are more efficient in computing. Okay. So I'm going to show you this article written by Irreducible, that how efficient the binary fields are. Okay, they are pretty efficient. So let's look at this. So in ZKSNARK, we have we used the field called the Mersenne prime, the 31-bit Mersenne prime, and this is how you design a multiplication chip for the Mersenne prime. So you have two input, and you do a 31 to 31 bit integer multiplier. The result will be a 62 bit. Then you have to do the modulus to get your proper result back. So why this is not good enough? Because you can actually have a carryless option. So by carryless, so what do I mean by carryless? Okay, let's look at this picture. So when we do I don't know if you already do the addition by hand. So this will be a very basic component in the hardware to compute a number in, let's say, Mersenne field, but whatever, like U32, so it will be a modulus addition and the edge step. So here will be your input, so this will be a bit, and there will be another bit. when you do addition, what you want is there's also the third input, which is the carry, the last carry you need. And this will be, in the end, this will be a circuit, and in the end, you get the result. And you also need to carry to the next position. So you will have, okay, so this, if you count, so they say, okay, this will be 5 gates if I count it correctly. And then, however, if you remember this, what we do here is XOR. So they don't need to draw it, just the one gate is the XOR, and it's done. So the second advantage is depth. So it means if you compose these simple gates into bigger gates to compute the big bits, then this binary field will give you much less depth. So what do I mean? Okay, let's look at, okay, I don't want to talk about in details about hardware design. It's probably nobody cares. Let's look at the picture. So this will be the Mersenne field multiplication. As you can see, it's very complicated, especially there's a lot of, I believe, okay, this is my arbitrary comment. So I believe the downside is the computing about sum of the base, and then you need these carries to carry everything to the next layer. So this is this, but for Binius, our binary field, what you do is you have this is 4 bits, and each of this will become one chip here, and in the end, this is 32 bit. Okay, so from the picture, what you can see is it's less complicated than this. Okay, so let's look at some numbers here. So in a 14 nanometer chip, so this is our design, and this here's the numbers. So this 32 bits binary field will have half. Here is the area, so the half the area, and that's the maximum level of logic. So which is the longest length in that picture that you have to go through number gates is 63, and this is 15. Okay, so in the end, this is the conclusion, is that if we do we have a hardware chip to compute a Mersenne field and the binary field, so the binary field will be 5 times more efficient. So yeah, however, what's the, of course we need to pay a price in how do we design how do we design a polynomial combinatorial scheme from this binary field? There's actually a lot of ingredients. So, okay, so there are actually 2 tricks. The one trick is that you can commit. Okay, I'm not going to go through the details why this is justified, but what okay, so I'm going to just describe in ideas how you do it. So if everybody who have done SNARK, you know that whenever you commit your data, you always commit in a elliptic curve point. So elliptic curve points are very big. At least the base field, they are around 250 something bits. So even you want to commit a bit, you still need 50 something bits. So this will be very big overhead. However, in binary field case, what you do is you can commit 1 bit into here, which is a 1 bit to 1 bit commitment. And what they call is that you can commit lots of your small data into the small bits, And because of this observation is that we can compose our small field into a big field element, and then we can do the big field arithmetics. So we can, which means we can use the packed result to do the commit here, and then get it back when we open it. Because when the field is bigger, the arithmetics is more efficient, which means you do more when you're in the bigger field effectively. So this is one idea. So they call it a ring switch. I'm not going to talk about in details how you do it. I'm going to draw a picture, and some of you have already seen. So here is our basis building block, which is Toyota. And you have this block, and H here is Toyota. The trick is here is you have here, say is okay, you can have here, you let me check what's the proper name of these things. So here what you get is two, there's lots of Greek and you have these kappas. The trick here is you commit in these small blocks, and you can actually use this. This is tau. So you can use this as a field element, and you can even use this whole thing, it's called a iota kappa tau, as a big field element. So you can use the whole data whatever you want, whenever it meets your needs. And this is the first ingredient they introduced in the Binius paper to make their first, what they call is, let me find the name. It's small field polynomial commitment scheme. Okay, so however they think, okay, this is not good enough, and then they introduce this IFRI-like new commitment scheme in the new Binius paper, which I'm going to introduce you another key ingredient they proposed. Okay. So they claim that, okay, we can do an FRI over this binary field. I'm going to introduce the key ingredients, and that's it. Probably we do not have time to cover the whole cooking So how to make everything together, I'm going to introduce a few key ingredients. Okay, let me, from here. Okay, so as some of you already know, if you want to do an alpha array, what you want is something called folding. And so it's not easy to, in prime field, what you have is called, what you have to is monomial, and if you do it on Ray-Solomon code, what you are doing is dealing with all the powers of sigma, omega, and that's called monomial folding. However, here we cannot have this so easily. Okay, let me introduce their definition of the FRI-like structure. Okay, here. So let's say we have a space. Let's start from S, which is S naught, and you will have a action called folding, which is Q, and in the end, this is a structure that you need to do the FRI. I'm going to tell what you can do. Okay, so they introduced something called the novel polynomial basis, which you will say will be a basis of. So let's start with this. So let L in then, okay, and consider that these are the polynomials that is degree is bounded by 2 to L, and the univariate polynomial. Okay, so the basis of this is naturally 1 and here they introduce a new basis so that you can do FFT. So let's fix I have two bases of L. Okay, here we also need L binary field. So which will be these betas. So what we are going to do is we're going to use these things to construct a new basis so that UI defined by span of these betas So as you can see, we are using more betas. These spaces will be larger, and in the end, there will be the full of L, and we use the subspace vanishing polynomial, which is just is defined by U in U I this. So which is everything. If you comes from UI, it will be vanishing on WI. So just pick everything UI and write this down. So effectively, if they come from something here, they will vanish. If they come from something outside here, they will not vanish. It will not vanish. And we take a normalized, this WI is defined by I by a value times beta I. So they will evaluate this thing is nice, so that they evaluate from here. Let's say there's a beta I somewhere, and they will evaluate from here 0 and evaluate here 1. You can see as they are nice in this. So there's also one more complicated thing is that we are going to create a basis from here by evaluating, by creating a bit complicated polynomials. So let's pick J from 2 to -1, and we write. So if let's say J is just, so we write it in bits, is J0, J22. So these things are just bits representative of J, and we define Xj. X will be a polynomial associated with J is equal to So the claim is that if you build this, then this polynomial will have degree J. And we will have a new basis of this by writing by this. So we will have a lot of polynomials if you do this, and we will have this. So this is our old basis. It's called monomial basis. And this is our new basis called evaluating basis. And this will be useful, and also this polynomial will be useful. I will show you how to build a folding from here. So what you do is we I'm going to show you how to start. So now let's our S0 be where we have binary field L with spaces and with a size parameter letter L in. I mean, you don't really need to take the notes. You can download the paper and check the paper yourself, because there's lots of symbols. And the rate parameter, capital R, in. Okay, so now we view these WS as linear maps from a L to L. So now since we have this S, I'm going to show how you project from, we construct these projections, and here is a projection. The projections are defining this. Our QI is so the claim is that the kernel of this, which means if something evaluated 0 by this map, it is included in SI. And so we have for I in L, so if we construct our big space here, and we cut down, and here will be, so we are reducing in the end. Okay, so here is something I provide you an idea of what is going on. So in the end, these are just projections. Even though the formulas are complicated, what is happening is just projections. So here what we are doing is justify that the projections, so if we have, this formula will be the projection, and the projection is something we want. Okay. Also, for H I in L, this Wi. So here what we show, so this is a show that if you want to go from here to somewhere here, you just do the evaluation of this W hat. And here the third one is, this is actually the compositions composed, which means that what's exactly happening here is that if you want to go from here to here, this is your S0, and it'll be S1. And if you want to go step by step, you use the compositions. And also is that if you do evaluation, and you will see that the rest. So since every step you kill one of these betas, and what they say is, okay, if you kill the rest, is a basis of your null space. So here is we constructed maps so that you can effectively go from here and here, and in the end we will provide a formula that is effectively the folding formula in FRI is this. And here is going to be our formula. So let I in this, and we have a map F that maps L. So if this F is just evaluating from here to your numbers, so L will be the numbers. And for each R, we can define the folding of F with R, which is defined by over Y is defined by the multiplication of these three matrices. Where this x0, x1 are just the fiber of y in S of qi inverse qi to y. So okay, let's go back to this picture. So what they are saying is that since here every projection we drop one dimension, so hy here will have 2 per image, which was your x0 and x1. And what they claim is that if we have everything used back, then this will be the folding you are searching in the FRI-like structure that you can build a folding scheme by this folding. And the rest of the paper, I guarantee you, is talking about how you estimate the security parameters from this formula and how you build the whole practice your scheme from this. So since we don't have time to go through the whole paper and tell the details, so I can guarantee you that beside that big object, which is the ring switch I tell you before, and with this will be the two ingredients for this paper that Irreducible published for how you construct a FI-like polynomial commutative scheme. Yes. So since we go through all the ideas, I think my talk just can end here. And thanks everybody for attending. And that's it today. Thank you. Questions? Yes?
Yeah, I guess just for my intuition again. So essentially we have smaller binary fields, which are kind of components or layers of
yes.
the larger, power binary field, right?
Yes.
So we are basically committing small size data to each binary field.
Yes.
We can then, because it's part of a larger, we can have arithmetics that we operate on the larger
yes.
fields, so we can have still this efficiency.
Yes.
And when you say the openings, we can still access all the data because we can actually
yes.
traverse down the towers to actually access all the data.
So the whole paper goes through why this thing is, even though it's free, you have to justify this is exactly what they want. It's kind of long and tedious, but if it goes through, it's just a mathematical representation of what you are saying.
And then basically you're just now proving how the fry works on these binary towers.
It's not exactly fry, but yes.
Okay. Not exactly.
Okay. I also want to mention, if there's last thing I want to talk about is that it's very interesting that these things, or I would say in this binary fields, this thing is a linear map. For any binary field, this x to x squared and anything you generated by this, they are linear maps. And this mechanism also needs this property because this is how when you compose, and here when you compose these, if I remember correctly, these QIs, they are linear maps. And when you compose the linear maps, you got linear maps. And this is something very nice, and I believe some will need this property. And yeah. Any other questions? Okay, thanks.